I'll be going over, yeah, today I will be going over some elementary models from scratch. And so this is basically the outline of what we'll be doing today. And to introduce, I think the main point of this lesson is to show that math modeling isn't just about getting the right results. It's about truly understanding what you're actually dealing with. And by doing so, you're going to be interpreting a real-world phenomenon in terms of quantitative results and clearly defining what you want to find and how you're going to find it. So good models, with that definition, can be justified to a very high level of detail. Basically, every little assumption and every little calculation used in the model should be justifiable with real-world evidence. And to practice doing so, it's always a good idea to build models from scratch, even when you know of an existing model which may apply, but you still want to understand how it actually works and how it is specifically applicable to this situation that you're dealing with. And so before we get into the problems, I'll introduce some guidelines. So what I'll do today is, first of all, of course, I'll go through these slides. I'll present some very basic modeling problems that you might have seen before, or you might not, and that doesn't matter at all. So, and if you have seen them before, you have to try to think about them again, maybe from a new perspective. And if you haven't done them before, I'll try to guide you to think about these problems from a fresh perspective. Then, of course, I'll be explaining these problems and I'll help answer any questions you have. Then, in the end, I'll provide one possible solution. And what you'll do is you can pay attention or you can do the problems by yourself. Basically, just attempt them before listening to my explanation. And also try to ask me any questions. And you can also ask me some random questions that you think I won't know, because then we will be able to discuss them together. Also, construct the model yourself. I didn't give the problems to you beforehand because I'll be giving a little bit of time in class. So you have a fresh memory of the problem right after you tried it yourself. Also, we are going to find other approaches and try to generalize the models afterwards. And some of them might be for homework or for personal exploration. And today, basically, we'll spend no more than 20 minutes per problem. And the aim of this is so that on each problem, we do not focus on too much of the technical details. We only focus on the general thought process and the ideas that go into solving each problem. We also are going to build problems and models using everyday knowledge. Of course, we're going to make the most effective models using the simplest math possible. And this is not saying that you shouldn't use advanced math, because you might have seen that many of the winning IMMC projects all use some very advanced tools. But that's because the problems there are very difficult. So if you're already applying advanced math to, say, some very simple problems, then you'll be using like graduate level math to solve advanced problems, which is, of course, not very ideal. And finally, we're going to go from real world situations to abstract models, and then use these abstract models to identify some details we have missed in those real world situations. So yeah, now I'll introduce the first problem. The first problem is rather simple. I think you have all heard of a population model. So this problem asks us to construct a population model to show the total human population or change in population of a certain geographic region over time. And I'll leave you maybe about 1 minute to think about this by yourself. And if you have any ideas, you can send them in the group chat. It seems like there weren't many ideas, which is perfectly fine. So now I'll be guiding you through this process step by step. Yeah, so I guess we'll start with a few questions. And here I've listed the first question is what are the main factors that affect population? And the answer I gave here is the current population, the birth rate, and the death rate. Now I think you can list many more factors like basically, yeah. Yes, you have listed some very good factors, and one of you gave a model here, which is really nice, but we'll see if we can derive that model later on. Yeah, death, morality, and migration. Those are all factors that will influence the fatality rate and also the birth rate and also current population, of course. So we can consider many more factors, such as education, maybe political structure, maybe the current environment in that country, like the natural environment, and things like global warming. But that's not the main focus of what our model is considering. Because if we consider all of those factors, we're going to get a very big and very messy model, and we can't really understand what's going on there. So for now, we'll try to keep things as simple as possible with these three factors listed here. And so how are these related? And I think the answer for this is sufficiently obvious. I think you should all be able to guess this without thinking about it too much. Basically, the current population is going to positively influence the future population, and the same goes for birth rate. And on the other hand, of course, if you have many deaths and a high death rate, the future population is going to be influenced negatively. So that's a very obvious correlation here, and it's a qualitative correlation that we can see before even constructing any model. Uh, yes, you have all listed some very good factors. And so let's see what factors can apply for the upcoming model. And so for the first problem, we're going to first consider a very basic model. So here we have some definitions listed. And with these definitions, we can consider an equilibrium equation. So basically what this states is that the increase of the total population in 1 year is equivalent to the birth rate minus death rate times the total population. Basically, the number of newborns minus the number of people who died in that year. So this is a very obvious equation, and it's going to be perfectly valid without too many assumptions. But now we set mu as a coefficient, and this is equivalent to alpha minus beta. But then we also assume here that mu is a constant. And now that seems a bit weird, but at first sight it is slightly reasonable because for most countries, the birth rate and death rate is relatively stable, unless you say there's warfare or famine or something like this. So if we assume it's constant, then the above equilibrium equation can be simplified to what we have here at the bottom row. And the final expression is an exponential function in terms of n. And so, yeah, this is what we get. But do you think this is accurate or maybe remotely accurate? Do you think it would work? Uh, Someone said birth minus death by 2. Yeah, yeah, it kind of works. And the reason it kind of works, I'm pretty sure you should all be able to think of this. It's basically because an exponential equation grows faster and faster. And it's going to get indefinitely large for larger values of it. And of course, humans have survived for like tens of thousands of years, but we do not see a very like anything close to infinity or anything above the magnitude of a few billion people. So that's something very strange, and I think we should be able to understand why. The problem is because we have set mu to be a constant, which is of course not true. And yeah, so the previous model wasn't realistic. And if we want to understand why, there are several factors that come into play. So first of all, if we run the model for a long period of time, then the region quickly becomes crowded. Now, with a crowded population, there are many problems that might occur. And so can you guys think of some problems and maybe list them in the chat? Like, so what would happen to mu if the population becomes crowded, and why wouldn't it remain constant? Yes, so some people said scarcity of facilities, and also pop country tries to stop birth. Yeah, some governments try to do that. Outward migration, yeah, rate may not be the same each year. Yeah, all of these are very valid reasons. And so right now I'll go over some of the more major concerns. So if you have a very big population, the resources in that country becomes depleted. And the competition between people for those resources is going to increase. And so, in general, there will be reduced personal satisfaction. And with the reduced personal satisfaction and maybe economic welfare, there will be less people giving birth to new babies. And on the other hand, since the population is already large, if um if if basically oh, someone said competition increases resulting in change in birth rate and death rate. Yeah, so that could happen. But the point I want to make about death rate here is that it doesn't really have to take more competition to lead to more death. Because let's say about P% of the population dies every year. And if that P stays constant, the death is going to increase as well. So it doesn't really take anything else, and the death is just going to continue rising every year. Of course, this model now is intuitively correct, as we know the population isn't ever going to be infinite. And so, if it's not going to be infinite and we have to bound this, how do you think we should do it? How do you think we should model mu realistically? Of course, we know like qualitatively it's going to decrease with time, but quantitatively, what factors should we consider? Yeah, well, right now, we consider that mu is in fact dynamic, and it actually correlates with beta and the number of people willing to give birth, B, and the probability of giving a successful birth, P. So basically, we retain the variable beta because that's rather fixed, and we don't want to change that up too much. But as for the other part, if we recall, mu consists of alpha and beta. So the alpha is going to be affected quite a lot. And this is what we see here. So basically, this expression is the same as what we had previously, but now alpha is decomposed into the form b times p, which is the same as saying that the number of people willing to give birth times the probability of giving a successful birth is the total number of newborns per year. And that makes a lot of sense, I believe. So this is valid without too many assumptions, but then after this step, we have to see how this is affected. So now we have two variables. We have b and we have p, and beta is basically constant, so we don't worry too much about that. But if we look at both b and p, I mean both of them could change with time. So which do you think is more significant? Okay, so there are mixed opinions. Some people say B, some people say P. Now, okay, let's consider P first, I think. Let's say if P changes, that means the probability of giving a successful birth is going to change. So how does that happen? I think one of the main factors that could happen is if suddenly there is a widespread pandemic or disease, and then like suddenly all the newborn babies die after they're born. I think that would cause a major change in P. But otherwise, I think most major changes would come from maybe like government policies, abortion rates, and also maybe hospital failures. So I don't think P is going to be that likely to change in the short run. Yeah, all these factors are actually going to affect B. While health is going to affect P, but health is not going to fluctuate by very extreme levels in a very short period of time. So most of these factors are still going to affect the number of people who are willing to give birth. So yeah, now we know that in this model, both P and beta are constant, but B is the actual variable we want to consider. Yes. And so mu can now be written as a linear function in B. And so now we want to see how B changes with the population P, like uppercase P. And now this is going to be actually very difficult. So here we made some very rough approximations. So here we make the assumption that resources are going to be depleted as the population increases. And this depletion is linear with the population increase. So with this in mind, we have the following equations here, which give an approximate equation for both B and beta in terms of uppercase P, which is the total population. And so this linear approximation is made, and it greatly simplifies the model we have made before. And with all this in mind, we can move on to the next step. If we combine all these linear approximations and we merge the factors like M1 and M2 together, we see that the general form is going to be mu equals negative k times large P plus another constant h. And of course, k is larger than 0 because we have to indicate that mu is decreasing as the population increases. Now, if we combine all of that, the model becomes something of this form, where mu is a function of n. And now we also find the increase in population becomes like this. And finally, we can write this in the form as follows. Can any of you see the difference between number 2 and number 3? There's a very subtle difference, and it's actually going to be very useful later on. So yeah, basically try to find the what makes 2 different from 3 and how this difference might be useful in a practical context. Okay, so I'll give you a hint. Like in the beginning, I think we mentioned that we will be going from models to real life scenarios to models, and then going from models back to real world scenarios. Page 35. Okay, sure. Let me see. Yeah, you mean this one? Yeah. Okay, so I'm assuming you're talking about point number 3. And I understand this is very vague. So basically, what I'm saying here is that as the population increases, the resources in that community or in that country or geographic region we're talking about is going to become depleted in a linear fashion. So we can use a linear model to describe the depletion of resources. And then if we combine all other factors, such as rationality and socioeconomic status, Basically, all of these factors are going to cancel out at all points of the spectrum. So with all of these cancellations, we can basically assume that the spectrum is going to follow an approximately linear distribution, or maybe a linear distribution with some kind of periodic fluctuation, such as a sine wave. And now this is going to be reflected in the following form below. Yeah, so here I'm not sure if you've heard of this, but there's something called Fermi estimation, which is very similar to what we've done here. Because we are actually estimating several concepts, and here it's actually infinitely many factors which may affect resource depletion and also the willingness to give birth. So we're assuming that the trends and the uncertainties or the errors in each approximation cancels out with each other. And even if they don't perfectly cancel well, they are already close enough to a linear approximation that we can assume it's linear in the end. Yeah. So this is something that cannot be described to a very high level of detail. At least, I do not know of any current model which can accurately describe this relationship. So if you have any more questions, I can come back here anytime. Okay, so if we go back, basically I'll explain this now because the third form is actually quite important, even though it's mathematically equivalent to the second form. So by converting the second equation into this final form, we see that there's this term over here, which is 1 minus Pn over m. And now this is very interesting because it shows when the population increases and when the population decreases. So what we have here in the denominator, which is m, is what we usually call a threshold population. And so if p goes above that threshold, the population decreases. And if it's below that, the population would generally increase. And if it's around m, then basically the population would remain very steady, would remain steady and would basically encounter small fluctuations around that point. So, like when P equals M, that's the optimal state for a country or something. Yeah. And as you may have noticed, the model we have here is discrete. It can only calculate time precision up to the quantity of a year. So that's not very precise. And so here we want to predict the population at every instant. And what we do now is something called analytic continuation, which sounds very complicated, but here it's actually rather simple. If we use the definition of limits, we can actually solve a differential equation, which gives us the very well-known logistic curve. And this is basically the continuous function that corresponds to the model we have just developed. And so, yeah, I'll wait for maybe 1 minute if anyone has any questions. Yeah, so as for the value of var and all these other coefficients, those are generally determined using data. So you can make another model to try to determine its value, but um, more generally, it's usually more convenient if you take like maybe one or two data points and substitute inside the equation, then you'll get the value of all these coefficients. Yes, that is the final answer. And you can express everything in terms of that final answer as well. So yeah, good job. R here is generally a coefficient, but if you want to interpret its practical value, it basically corresponds to the willingness of a population to reproduce or give birth to future generations. And so R can be generally used as an indicator of a population to see their general level of overall satisfaction and well-being. Yeah, that's basically the meaning of R. Could we assume anything different than linear distribution? Yes. So, another common model which is used, which also fits our assumptions, is a linear distribution, which is modulated by something like a normal distribution. So it's a linear distribution, but it has a slight peak at one of the values on the distribution. And that is caused by, as we all know, because most humans are very similar to each other, and only a small fraction of humans think very differently from that major group. So we consider the main portion of the population and then the outliers. It's going to be a linear distribution modulated by a normal distribution, which has a slight peak near the middle of that function. But the problem with that is going to be much harder to compute, especially analytically, uh, because something like the normal distribution cannot be integrated analytically. And here, of course, we can solve this differential equation, which is one of the main advantages of using a logistic curve. Yeah. So you can always use some more advanced functions or a normal distribution, but that's going to make it harder to solve. So we generally try to keep the model simple using a simple linear approximation when it's sufficiently close to the actual value. Yes, it is enough. But if we do want higher levels of precision, because this might be able to approximate the population to an order to the same power of 10, or maybe to one magnitude less. But if we want to, say, achieve higher precision, maybe precision to like 10,000 people or 100,000 people, then we might have to improve this model further. And by doing so, we might have to sacrifice the computability of this model, and we might have to use some approximations or some computational software instead of solving it analytically. Yeah, so for models, no models are exact representations of real-world phenomena. All models involve some sort of approximation, but it's usually a trade-off between convenience and also the practicality of the model and also its precision. So if we want to have a more practical model, yeah, I think precision and understandability are actually highly correlated because a very precise model is going to be very understandable. Unless you say something like you're going to use a polynomial regression and use a 10th order polynomial, but I don't think you would be considering that anytime soon. So most models, for the majority of models, higher precision is also corresponding to higher understandability and more detailed interpretations. Yeah, in making a model, you have to consider situations or data with variables because in mathematical modeling, we're considering quantitative models that can be solved using math. So we will need some data. Uh, if there are no more questions for now, I guess I'll move on. So here is the second problem. And of course, we'll begin with the problem statement. Okay, I'll read it. So basically, it asks us to model the population of a honeybee colony over time. So it's in some ways it's very similar to the problem we just did, but that was with humans and this is with honeybees. So there are quite a different mechanic for this problem. And also, here's a note. So this was actually borrowed from the 2022 high MCM, but the problem, like the original problem, was very difficult. So basically, this is a more simple version of the first question in that larger problem. And yeah, so for this problem, we'll focus on a rather basic model compared to most of those official solutions that involved a lot more advanced mathematics. Computational math, yeah, I just saw this question. But yeah, for computational math, it's not something that you need to make the model. Like the models we just did, we constructed the model without any computation. Like we did all the problem solving by hand. But for computational math, it's generally necessary to use that to assess your model and to determine whether it's valid. It's also going to be very beneficial when you're doing fine tuning. So if you want to achieve higher precision models, as we've said, there's usually no analytical solution. And so you're going to have to use some computational software. The most basic, I think, is Mathematica. And with that, you should be able to solve most numerical differential equations. And that basically allows you to use much more advanced math when creating complicated models. But for such basic models, I don't think it's very necessary. Yeah. Um, and so I'll go over the preliminary analysis quite quickly because we have already done something similar before. So we know that it's affected by birth rate, death rate, and also the current population. But the question is, can we use the logistic curve from before? And the answer I already gave it to you here. It's no. And do you think you know why? I mean, if you know why, you can say it in the chat. I'll probably wait for another minute. Okay, so I'll give a hint. It's not because we want to do the model from scratch. Even if we were like doing this for a competition, we can't directly apply the logistic curve. It would be very bad. Yeah, that's a major factor. Do you know how they aren't the same? Because before we only identified the relevant factors. We didn't actually compute the final numbers and coefficients themselves. So what's the difference between bees and human births? That's going to be very useful later on. There's no will of honeybee whether to give birth or not. Well, they're not affected by will, but they're actually affected by some other factors, which also govern how and when they give birth. And yeah, they need a queen bee and they don't have the same rates. That's all like based on the results. But like, why does that occur? And how does needing a queen bee change the reproductive process? I think those are questions that we have to answer later on when constructing the model. So I guess we should begin. Yes, we may need to consider some more complicated factors like different time periods, different weather conditions, and different types of bees. Uh, Someone said mating flights. Normal population doesn't affect the birth rate. And also, queen bees lay eggs in a specific season. Yeah, we'll see about that later on. Okay, so here, uh, bees population birth rate isn't linear. Yes, that's true. Yeah, I think those are all factors that we should take into account, and we'll see how everything goes. So here we've defined B to be the total number of newborn bees from year 0 to T, where we define 0 by ourselves. Here we also assume that the laying rate of the queen bee remains the same. And it's actually typically the same without consideration of the weather conditions. So we will assess that separately. So first of all, we begin with a basic model, which assumes that the laying rate is the same all year. And it tells us that the change of bees with time, or the newborn bees, is going to be 365 times L times R, where here we have said that L is the maximum number of eggs laid each day, and R is the percentage of eggs that will eventually lead to offspring. And let's see, I'm not sure if there are more questions at this point, but I think, okay, no questions. Yeah. So, but this is not a very effective model because, as you've all mentioned, the laying rate is the same for similar weather conditions and similar time periods, but across the 4 seasons, it's going to vary drastically. Because in the winter, the queen bee produces many less eggs than during the summer, let's say. Yes, we haven't gotten to death rate yet. We'll do that later on. And so with this birth rate, it's going to be varying significantly throughout the year. And in months with decreased pollen, as I've said here, it's for approximately half of the year, the number of offspring is going to decrease substantially. Of course, similar to how we've used a linear approximation before, now we use a periodic approximation. We create a periodic approximation term, and this is by using the sine function. It's basically the simplest periodic function that we can find. So, if you have any questions about this correction term, I can answer it now, or I'll move on. Okay. Yeah, please elaborate. Okay. So what we do here is we multiply this correction term onto the previous expression, onto the right-hand side. And what this tells us is that we see that this function has a period of 1, which here, since the time unit is years, it has a period of 1 year. So it basically shows how the model and how the number of bees and the number of new eggs laid varies across the 4 seasons. And of course, here we also see we added 1 to the end of the sine function. That is because we're only considering the number of newborn bees at this period. We are not yet considering the deaths because we'll do that separately. So we want to ensure that the newborn bees and the number of newborn bees remains non-negative throughout the year. We also divide by 2 for rather obvious reasons because we don't want to accidentally double the maximum number of eggs by not dividing by 2. Yeah, hopefully that makes sense. Actually, the next slide provides further elaboration on this function because, this periodic correction term actually feels very weird because actually a piecewise linear function does the same job as what we've just stated. And so can any of you think of reasons we should use a sine function instead of a piecewise linear function? Yes, easier integration. That's a good answer. But what if, let's say, if we find out in the end the model needs to use numerical integration, and we cannot even integrate this model using a sine function. So then the benefit wouldn't be integration anymore. And also because sine has periodic functionality. But actually, many more functions are periodic. And as I've said, the piecewise linear function can also be defined in a periodic manner. So there are some other advantages. And you can think about how this corresponds to a real world scenario and how bees interact with each other. There's something about the how bees pollinate and reproduce that is actually modeled very well using a sine function. And I guess I'll show this right now. So when no detailed explanation is possible because we cannot know whether it actually fits the sine function, we try to test if this function aligns with the foreseeable factors that we can actually assess. So for instance, based on the behavior of bees, how should the derivative of this periodic term behave? Do any of you know? So let's say maybe near t equals 0, t equals 1, t equals 1/2 during the spring. How should the derivative of this correction term behave in an optimal situation? T divided by 12? I meant to say like t at t equals 1/2. So what do you want an optimal term to have? Well, I think maybe we can try to do something together if I can manage to draw on this thing. Yeah, I can draw on this thing. So when t equals 1/2, that is going to be during the spring, right? And during the spring, they reproduce a lot. And so when they reproduce a lot, there's going to be a period where it plateaus because, it's not going to be going like this, right? That's going to be, uh, may I ask why you added 23 at the end? Sorry, maybe I'm not understanding something correctly. Like, oh yeah, 2/3. 2/3 is also a bit, um, okay, I don't quite where 2/3 comes from, but I do understand if you add something within the sine function, I think that would make more sense. Because, like based on what we already know, the sine function is like this. It goes from 0 to, and up to 1 and down. But then, like for the bee colonies at 0, let's say it's during the winter, we obviously want it to be at its lowest point, which is like something like this. So I think a horizontal translation should be reasonable, but I still don't really get why you added 2/3. Uh, well, maybe we'll worry about the 2/3 later on. Yeah. So basically, as you can see, let's say during a period in spring, let's say this is spring. This box, no, okay, that's not a box. So let's say one of these curves represents the spring area. And if we replaced it with a linear function, it would look something like this. Of course, the linear function also works, but of course, in spring, it's not going to decrease so sharply after this one instant. It's going to remain at a very high level of pollination and a very high level of reproduction for some time after the peak of spring has passed. And even as it starts to get colder, it's only going to decrease very gradually. So something so sharp like a linear function is not going to work because its derivative is too large. And its second derivative is also constant, which no, its second derivative is 0, which isn't what we want here. Yeah. So we want a second derivative that's preferably negative and changing very slowly, so it can represent the gradual change and conversion of the bee colony. And yeah, that's basically one of the factors we consider. And now this PowerPoint is kind of broken. But yeah. So for instance, how should the derivative of this periodic term behave? And where should the widest part of the function occur, as we've just said? Yeah. Yeah. So, but yeah, your question is if the birth rate goes below the x-axis, wouldn't it be negative? So if we look back at what we derived as the correction term, we see that we've actually added 1 at the end of sign. So that is to ensure that the correction term doesn't go below 0. And even if it stays at 0, I mean, if it stays at 0, it still makes some sense because during winter it basically does not reproduce at all. So yeah. Was the previous model accurate? I mean, here, of course, it's not accurate because we neglected the fact that a colony's carrying capacity is limited. So, I mean, we are going to derive some death rate analysis, but even then, if the death rate analysis doesn't go well, and maybe the queen bee just likes reproducing a lot, then maybe they'll reproduce like 100,000 bees in a short period of time. And then the colony would be too small to fit that many bees. So if this happens, we see that the extra bees, would have to be kicked out of the colony, and basically there would be extra deaths and also decreased birth rate. So let's say if the maximum capacity is W, we can derive a logistic model as before for the increase of the honeybee population. And that is the importance of the W term, because if you recall what we did before when deriving the logistic model, we considered that the maximum capacity as a term in the denominator, which we also called the threshold population when considering humans. So that is the same W that we used before, and we see it's very, very important now that we consider a honeybee population. So, of course, here we did not derive the model from scratch, but as practice, I highly suggest that after leaving this class, you try to derive this yourself from what we did before and basically using the same logical flow. Yeah. And this is the final birth rate model that we will consider. Uh, any questions? Yes, of course. I'll send all of the slides. And as for the death rate analysis, it's actually very complicated, and we will only do a qualitative analysis. So here we see that bees are very active creatures, and so they're so active that in fact even their natural deaths are caused by overworking. There are also several factors to consider, which is other than overworking, there are deaths due to diseases and also death due to predators. In addition, there are two types of bees that we have not discussed before. One type is called forager bees. Basically, these bees constantly leave their hive in search of pollen, and they're exposed to very different conditions every day. And non-forager bees basically stay inside the hive and stay near the rest of the colony, and they do relatively little work compared to the forager bees. So yeah, with these considerations, we have to consider both types of bees separately when analyzing the deaths due to disease and predators. And so now that's basically the end of the lesson. And so now I'll go over some key takeaways. So first of all, there's a very basic principle of modeling that you should always try to justify a mathematical model from the very beginning, whether it's a very simple model or a model involving very advanced math. And modeling is not just combining existing models. So even let's say if you knew the logarithmic model and you knew the logistic model, you should not just combine them to make another, you know, natural death and death due to overwork. What if the queen bee died? Wouldn't the colony just end there? Maybe the bees would go searching for a new colony. Hmm. Yeah. So things like this are outlier situations. We could just say that maybe suddenly a meteorite fell on Earth and all the human died. And so that would also not fit our human population model, but it's also something that's too random and chaotic to consider. If the queen bee did die in that instance, the other bees would maybe just die, or if in a more optimal situation, they would find a new colony. But in most cases, I believe they eventually die out, or they also find a new queen bee in place of the original queen bee. But in most cases, that new queen bee is not sufficiently mature to take over the throne. Yeah. So there's going to be a major decrease in reproduction for a short period while the new queen bee gets accustomed to reproducing and creating new bees. Yeah. Okay. Are there any questions still about the bees model? Well, the correction term actually accounts for all four seasons. It's going to be a continuous change because you see, I think I'll just draw on this slide. Yeah. So let's say spring starts at the peak, then it slowly decreases, and at the peak of winter, it decreases to its lowest point. So basically, what the correction model does is that it ensures that basically the number of newborn bees every day reaches some value close to zero during the winter and reaches some value close to the maximum value during the summer. Do you mean the constant correction term or the correction function? Because the correction function is to account for the seasonal change. And the correction term, like the number that we added in the end, by adding one, is to make sure the birth rate doesn't get down to negative values. Okay, maybe I should go back to that slide. So here, yeah. Here we see we added a one in the end. That's a term, but then we also have this entire correction function. So this one is added to make sure the function doesn't decrease to negative values. Yeah, you're correct. Okay, so I'm guessing there are no more questions. Yeah, if there are no more questions, I'll go on. So it's more important to understand how a model works rather than focusing on the results. But both are very important. So if possible, you should achieve both. And also impossible, try to use simple math. And as for the procedure, basically, this is a brief recap of how you should approach the modeling process, at least for basic models. The modeling process is generally logical, and if you have done Olympiads before, you'll find it's actually very different from what you do in math Olympiads, because in math Olympiads, you need a lot of uncontrolled abstract thinking. But here, it's more like rigorous sequential thinking, but also very abstract. And you should be getting used to going back and forth between highly abstract equations and real-world interpretations. Because when you're creating a model, you should never detach yourself from reality. But you should also never use too much qualitative interpretations because you're trying to assess some phenomenon using mathematics. And then if we go on, okay, this presentation. Yeah, it's basically the assumptions and variables, as you've all seen, don't have to be perfect. At the beginning, we actually missed quite a few assumptions, and then we came back and added them on. Yeah, quantitative analysis is always better for the models, but if you're doing quantitative analysis, you have to do some qualitative work beforehand. So such as what we've done here, we always like before we actually analyzed the equations, we always used a preliminary analysis where we used some quantitative models to consider the influential factors and how we can define the variables and stuff. So quantitative analysis is what we are reaching for in the end, but qualitative analysis is part of the process that actually gets you there. Yeah. And how do we describe negligible possibilities like the death of the queen bee, which I mentioned earlier? If you believe like the general influence of the possibility that we're considering is actually less than the precision of the overall model, then you can just ignore it. But if it's greater, like if it's at least a magnitude greater than the precision of the model, then you should actually consider that factor. And by considering that factor, usually you have to construct another model because it usually defies many of the assumptions you've made when creating it. So hopefully you won't encounter that type of problem in modeling because it's going to be very tedious. Yeah. Um, that's the end of the presentation. So if you have any more questions, you can ask them now. Okay, yeah. The correction term is confusing. Uh, I could not find a better way to model this, and I also read a few papers, but all of them could not explain how to derive a correction term. So this is the best correction term I could think of. And it basically relies on some empirical evidence and also some qualitative approximations that are merged to form an approximate quantitative relationship. So it's definitely not going to be very precise, but I think it does the job, at least predicting the trend in the long term. Um, okay, so this question is very long. For example, a building constructed in Japan could use earthquakes. Yeah, oh, yeah. If you're considering a specific geographical region like Japan, that is definitely not a negligible possibility. So in that case, you should add it. But if you're, I think even in the US, if you're designing a structure, you have to consider earthquakes as well, because there are earthquakes in most parts of the world, just not as severe as the ones occurring maybe in Japan. So yeah, I don't think that can be neglected. The question didn't mention geographics. You should still consider it because like some models are more high risk, high stake. If you neglect a very small factor when constructing a building, it could be leading to the loss of lives. So things like this require a much higher level of precision than if you're simply calculating a very basic B model. How do we integrate the earthquake possibly? Isn't it super random? Um, if we're predicting when the building collapses, then it's going to be super random. But if you're like designing a model to prevent earthquakes, like to ensure that the building can withstand some very intense earthquakes. Then you can like say assume that the earthquake is a very high, very strong earthquake. And then with that assumption, you can predict how the building will vibrate with that strong shake and how measures can be implemented to mitigate that vibration. So for things like this, you usually assume the worst case scenario, and then based on the worst case scenario, derive your final solution. Okay, so I don't think there are any more questions. If anyone has another question, you can send that in the chat or maybe just send me a message on Discord and I'll try to answer it. Yeah. In IMMC, we gotta solve these kind of no, this is just as the title says, it's a basic model. It's elementary, simple models, and we're just introducing them to show you the idea of modeling and how we can apply modeling to real world problems. So what you'll be doing in IMMC is going to be a lot more complicated than this. But if you do this, you can basically, I think if you do what I've shown today, you should be able to get something around an honorable mention. Yeah. But if you want to get a very high award, this is definitely not enough. Yeah. Yeah. So when starting your model, you should neglect as many factors as you can. And then, like when you're constructing the model and you see that some factors are insufficient, you should then add those factors back on and reduce your number of assumptions. Yeah. So basically, start with something simple and build upon that foundation and slowly get to something very complicated and also considers a wide range of factors. Okay, thank you.